everyone's ready, I guess we'll go ahead and get started. So my name is Veronica McGowan.
And I'm Brandon Parrish.
And we are co-team leads of the Genesis project. Just a little bit of housekeeping before we get started. We are going to be giving you guys a dual screen presentation. So when we focus your attention to the screen on the left here, this is the primary screen or screen A. When we focus your attention to the screen on the right, this is the secondary screen or screen B. So Genesis's overall mission is to make space more accessible for both individuals and companies by sending small satellites to low Earth orbit. We'll be doing this with our vehicle, the Ambassador, seen here on the primary screen. The Ambassador is the second stage in a two-stage to orbit system. The first stage is being designed by Launch Tech. It's called the PT-1, and you just heard from the group previously right before us. So you can see configuration of both the PT-1 and the Ambassador on the secondary screen mated together. Due to the uniqueness of this project, we have both astrodynamic and aerodynamic students working on this. So just a quick run through of introductions for our astrodynamic students. We have Wesley Goldner-Carver, Neil Noonan, and Morgan Cherry. And you can see the respective responsibilities for this program right up on the primary screen.
And now I'd like to introduce to you the aerodynamics team seen here on the secondary screen. We have Eric Lopez, Chris Crawford, Michael Rosnick, and Nick Langenegger. And now up on both screens you can see just some talking points we'll be discussing today, but essentially we'll be reviewing the preliminary design of our Ambassador spacecraft.
So a little bit of motivation on why we decided to do this project. So according to the Commercial Space Transportation Forecast, the small satellite market is going to be at a maximum over the next 10 years. In addition to this, all of the current launch options primarily focus on larger payloads, as you heard from Kyle previously. So there's not a lot of competition in this market right now. And because these other vehicles are not reusable, that drives up not only cost for the launch, but also time in between launches because they have to manufacture a new vehicle every single time. So what the market needs is a low-cost, reusable, and reliable space vehicle.
So now in order to fill that need, NASA and the DoD put forth an RFP outlining requirements to design a reusable spacecraft. Those requirements are shown here on the primary screen, or the key requirements. Now, the Ambassador is being designed to fit those requirements, but it also has to meet certain FAA requirements because it is a commercial launch system, and those requirements are shown here on the secondary screen. Most of the FAA requirements involve just keeping the general public safe during all of our launches. And now shown is the mission profile for the combined mission of both the PT-1 and the Ambassador. Phases 1 through 5 show the mated flight, or taxi, takeoff, and cruise to launch of both vehicles. The asterisk denotes separation of both vehicles, where 6 and 7 is return to base of the PT-1, and phases 8 through 12 involve the climb to orbit, release of the satellite payload, re-entry, and glide to a runway landing of the Ambassador.
So when first coming up for our original design, we wanted to look at other vehicles currently in the market. A couple air launch vehicles we looked into were Pegasus and Launcher One, and you heard a little bit about their first stage from Launch Tech's presentation. It's important to note that the second stage vehicles are not reusable, so that's going to drive up that cost and that time in between launches. Another vehicle we looked at, although it's not air launched, is the Space Shuttle Orbiter. So although it wasn't air launched, it was very similar to our vehicle in that it re-entered the Earth's atmosphere and landed on a runway. So it was considered a reusable vehicle. So we got a lot of information from the space shuttle in order to come up with our design. Another vehicle that's not mentioned here on the screen, because it was a classified project, the X-37B, although it's similar to our vehicle, we couldn't get much information on it. However, it was taken into consideration for aerodynamic purposes. On the secondary screen, you can see a size comparison between the Ambassador and the Space Shuttle. We are about half of the size of the Space Shuttle Orbiter, just to give you guys some perspective. On the primary screen, you can see a weight breakdown in comparison with all the other vehicles we compared it with in the market. And on the secondary screen, you can see a cost breakdown. Now, because we are a reusable vehicle, we are going to be the cheapest option in the market at $8 million per launch.
And so now, these are some design configuration choices that Genesis made when first coming up with the design of our vehicle. Firstly, we're using 2 liquid rocket engines. They're Pratt & Whitney RL-60s. It was a program developed back in the early 2000s. We are going to be unmanned. We have a low and wide fuselage, giving us lifting body characteristics. And we also have a highly swept delta wing and a V-tail configuration. Now, an overall aircraft 3 view is shown here on the secondary screen with the vehicle's dimensions shown. Now I'd like to invite Wes up to talk about the layout and design of our fuselage.
Thank you very much, Brandon. So I'll be going over the layout and design of the fuselage as well as the payload bay. So our RFP designates that we have a maximum weight limit of 75,000 pounds. So we opted to go for an unmanned design. This saves us weight on systems such as life support systems and pressurized cabin for human spaceflight. Then this drove our design to just fit around the tank system that we have on the Ambassador. As our design went on, the fuselage became a little bit bigger due to the extra structure we added on the inside to account for torsional and bending forces that we're going to see. Third of all, we have an electronics bay that will be controlling our flight systems because we are unmanned. Now this electronics bay, as you can see on the primary screen, is located around the fuselage. This will be on both sides of the fuselage. This will have systems such as flight computers, telemetry data, transceivers, and responders. So now going into the payload bay, a couple of characteristics are seen on the primary screen of how we designed this. The main thing is we wanted to be viable in the market, so we have two payload bay configurations. As you can see on the secondary screen, we have a single payload bay configuration meant to carry our maximum payload of 332 pounds, and then we have a multiple payload bay configuration that we can carry multiple small satellites in. This payload bay also needs to be easily accessible, so it's placed towards the top of the Ambassador spacecraft. This is for ground crews to perform maintenance on the payload bay when necessary, as well as install the payload bay easily. Our door system for this will have a two-door system on the top that will swing out when we are in orbit and ready to jettison the payload. The two doors will be electronically latched, and they will have a hinge system attached to the payload bay. Now, the materials for the payload bay will be aluminum, which will be for the attachment and deployment system, which I'll be discussing in a second, as well as carbon fiber reinforced polymer. The box itself will be made out of the carbon fiber. So now going into the attachment deployment system. The top plate is going to be bolted to the satellites. This is similar to how the Pegasus launch system does their satellites. This top plate will be attached to the bottom plate with a C-band clamp that has a remotely activated pyrotechnic charge that will be activated when we're ready to release the payload. In between both of the top plate and the bottom plate, as you can see on or in between the top and the bottom plate, there will be retention springs as well. Now, these springs are in compression when they start, and then when the C-band clamp is released, the springs will become out of tension and push the payload out of the payload bay. So, now I'd like to invite Eric Lopez up to discuss the layout and design of our wing.
Thanks again, Wes. Now on the primary screen is a list of some of the key information we chose going into the initial design, or our design of our wing. We had to research some pre-existing reentry vehicles, and they're shown on the secondary screen, the X-37B and the Space Shuttle. This assessment of these two vehicles led to our conclusion of having a highly swept delta wing. We also incorporated a conic leading edge. This is to help distribute the heating upon reentry. We also went with about a 50 pounds PSF wing loading. This is lower than our initial 60 PSF estimates we came up with. This is due to the fact of reentry vehicles. They claim to have a lower wing loading. This helps distribute the heat more upon reentry as well. On the primary screen, we went with a NACA 0010 for our airfoil. This is in our root and throughout half of our wing. This has been used on the space shuttle, so it has performed throughout the various phases of flights. We will see a hypersonic into subsonic. On the secondary screen is the airfoil we went with for the tip of our wing, a NACA 0016. This is to allow that our thickness throughout the leading edge of our wing remains a certain thickness to allow for the proper amount of TPS system to be equipped to it for re-entry purposes. On the primary screen is a platform area of our wing. It comes out to around an area of about 230 feet squared. It has an aileron that expands the full length of our wing. As you can see, in order to analyze the wing, we had to break it down into a 60-degree delta wing. with a aspect ratio of 2.3 and a taper ratio of about 0.15. On the primary screen is a lift curve slope for our wing. This is created by turning the 0010 and the 0016 NACA data into the lift curve slope you see in yellow triangles. On the secondary screen, to further analyze, we did a lift curve slope at Machs 1, 2, and 3. To note, as the Mach number increases, the CL alpha and the CL max both decrease. On the primary screen is a flight envelope for our vehicle for landing at sea level. The Q limit shown is driven by the landing, our landing. It is the highest speed at which we want to land at. Also to note, since our payload is such a small percentage of our overall landing, if we'd have to come in landing with the payload attached or still in our payload bay, it has a very minimal effect on the performance of our flight characteristics. On the secondary screen, note they have a stall lines for our vehicle at 40,000 feet. For various other phases of flight, our Q limit is theoretically up to around Mach 20. So it's not shown in this graph. But what analysis has shown about at 40,000 feet, our forward velocity is estimated to be somewhere around about 250 knots. So this graph shows that around 40,000 feet, we may be able to gain some sort of lifting characteristics of our wing. And now I'd like to invite Chris up here to talk about the empennage and stability control.
Thank you, Eric. So as you can see on the primary screen, these are 4 of the designs we considered for the empennage. The 2 primary ones I want to focus on are the vertical tail and the V-tail. We initially decided we were going to go with the vertical tail configuration. However, after estimating the effects of the fuselage and the stability of the aircraft, we decided to go with a V-tail to increase the longitudinal stability. On the secondary screen, you can see a size comparison of the Ambassador with the X-37B, along with some dimensions of some parameters of the V-tail. The V-tail features a NACA 0012 profile and also is an all-moving control surface. In addition, some advantages of this is that the V-tail removes some of the downwash effects of the wing and also removes the tails from the fuselage blanketing effects. On the primary screen now you can see a dimension drawing of one of the V-tail sections. Some important parameters of note are the dihedral angle of 28 degrees, the aspect ratio of 7.55, and the planform area of 145 square feet. On the secondary screen here you can see a CL alpha plot of the V-tail section, and as you can see the CL alpha is about 1.13 and the stall angle of attack is about 16.5 degrees. So here on this primary screen you can see a longitudinal X plot of marking the stability of the Ambassador. In our most critical condition we have a static margin of 1.2%. This is relatively low, and to compensate for this we've added a flight control system to allow better control of the sensitive static margin. On the secondary screen you can see the directional stability of the Ambassador. Because the longitudinal stability drove the size of the horizontal aspect of the V-tail, this also affected how the effective vertical tail area was shown to be. According to Roscom, a CN beta value of 0.001 is sufficient to maintain static stability of an aircraft. This would have produced a effective vertical tail area of 41 feet squared. However, because of the driving constraint of the longitudinal stability, this increased the size of the V-tail of effective vertical tail area to 80 square feet, giving a CN beta value of approximately 0.0049. Now I'd like to welcome Neil Noonan up here to talk about the propulsion system and reaction control system.
Thank you, Chris. I'll be talking about the propulsion system, and this includes our engine selection, our tank design and layout, as well as our reaction control system. So in selecting an engine, on the primary screen you can see some of the parameters we looked at. First we needed a high ISP, or specific impulse. This is efficiency of the engine, or it can be thought of as like miles per gallon. A high specific impulse allows us to have a lower amount of propellant mass, and more of our overall vehicle mass can be structural. We also needed high thrust from these engines. When we are dropped, we want a thrust to weight ratio greater than 1. Then we also need a low mass for these engines. This is so that the mass of the engines doesn't cut into our structural mass too much. We also wanted a high engine lifetime because we are reusable. We do not want to have to replace these engines every single time we fly. On the secondary screen, you can see some of the engines we looked at. We looked at almost every existing engine and evaluated them with the parameters I just described. We first originally chose the RL-10. This was designed in 1950 with some small subsequent upgrades since then. We determined that to get to thrust to weight ratio greater than 1, we need 4 of these engines, which provides more points of failure for our design. It also has a lower ISP, so we determined we needed more structural mass, so we needed to find a more efficient engine that produced more thrust. We looked at the existing engines and we found the RL-60. This is an engine that was being designed in 2002. It passed its critical design review. It was being developed, a test article of this engine was being developed in 2003, and that's the last that was heard of it. But it does give a good idea of what an engine designed today could do with the improvements in technology. So we used the RL-60. The other thing to note with these engines, they are second stage engines. To get that high efficiency, they have large nozzles. Large, long nozzles is not good for these rocket vehicles for their length. So they actually cut these nozzles in half, and the lower part of the nozzles are stored above them and extend down upon stage separation. This has direct effects to the lifetime of our engine. For the RL-60, for the RL-60, the lower part of the nozzle has a different cooling method than the main part of the engine. It's radiatively cooled, and we have to replace it every 4 launches. The main part of the engine is regeneratively cooled, and we can replace it every 16 launches. Now I'll talk about our tank design. For our tank design, we need to store, for our propellants, we need to store liquid hydrogen and liquid oxygen. That's what the fuels the RL-60 runs off of. We know that spheres are more structurally efficient, but to get a better aspect ratio for the overall vehicle, we decided to go with cylindrical tanks with spherical ends. We also decided to make these tanks out of carbon fiber only. This is a technology that is being developed by companies in the market. On the primary screen, you can see some of the dimensions for our hydrogen tanks, and on the secondary screen, you can see their location in the vehicle. Now I'm also going to talk about the oxygen tanks. They have the same designs, cylinders with spherical ends. On the primary screen, you can see their dimensions, and on the secondary screen, you can see their location. When the vehicle is being launched, we need a pressure gas to backfill those tanks and make sure they remain structural. For this, we used helium, which is an inert gas. You can see on the primary screen our helium tank dimensions. We decided to move the volume into. We decided to make them spherical tanks to make them more structurally efficient, lower the mass of these because these pressure tanks are at a much higher pressure than the propellant tanks. We also decided to split them into 3 separate spheres. This allowed us to push the 3rd sphere out, as can be seen on the secondary screen, to provide room for the payload bay and electronics bay. Now I'm going to talk about the reaction control system. When we're in space, there's no air to move over our control surfaces, so we need to have a way of controlling the attitude or orientation of our vehicle. For this, we decided to use cold gas thrusters. You can think of these as scuba tanks with nozzles on the end. And we needed to choose the gas for this to provide a large enough thrust. We wanted a high ISP for our cold gas thruster so that we could minimize the amount of propellant needed. So you can see on the primary screen a few of the gases we looked at. 2 of them we already have on board, the hydrogen and the helium gases. However, we decided to go with helium even though it has a smaller ISP because it has a larger density. It allowed the RCS tanks to become smaller. Now I'm going to talk, and then you can see on the primary screen the important dimensions of these cold gas thrusters. Important to note, they're 25. Each thruster provides 25 pounds of thrust for 5 minutes. On the secondary screen, you can see their locations. We're going to have 16 thrusters. it, 8 in front as in the orientation scene, and 8 behind the CG. Now I'm going to talk about the tank installation. The fuels we're using, liquid oxygen and liquid hydrogen, are cryogenic. It means they're stored liquid at very cold temperatures. We need to make sure that our fuel doesn't boil off as it heats up and is transported on the PT-1. So we are using Cryogel Z to insulate the tanks and make sure they remain that temperature necessary. Now I'd like to invite Michael up to talk about weight and balance analysis.
Thank you, Neil. So some of the overall mission weight estimates are shown on the primary screen. The takeoff gross weight is just under the RFP requirement of 75,000 pounds. Most of this weight is accounted by fuel. The landing weight of the vehicle is just under 11,500 pounds. On the secondary screen, you'll see some estimates for the fixed equipment weight of the Ambassador that includes things like our flight computers and our actuators. The methodology for determining the weight and balance of the Ambassador was to take the weight estimates for each system and moment arms generated from the CATIA model and sum those together to find the total center of gravity for the vehicle. This was done for 3 flight conditions, which are shown up on the primary screen. On the secondary screen, you'll see the weight and balance station diagram for the Ambassador. In the fully fueled configuration, we have on the primary screen a percentage breakdown of the weight of the vehicle. Just under 85% of our weight is accounted for by the fuel in this configuration, with the next highest percentage being the structure at just under 5%. On the secondary screen, we have a more detailed breakdown of this weight, including the CG locations for this condition. Now on the primary screen, we have the percentage weight breakdown for the empty or landing configuration. These weights are much more reasonable for an aircraft, with the highest percentage being the structure at just over 26% of the weight. This is followed closely by the fuel tanks and by the engines. On the secondary screen, again, we have a more detailed breakdown of the weight, including the CG locations in this condition. Now, on the primary screen, we have the CG excursion diagram for the Ambassador for a typical mission, which will start in the fully fueled configuration. The Ambassador fires its engines and proceeds to space, deploys the payload, and will return to landing in the empty plus no payload configuration. As you can see, in all of these phases of flight, we have a positive static margin with the center of gravity forward of the aerodynamic center. Now I'd like to invite up Eric to talk about the drag polar analysis.
Thank you, Michael. On the primary screen, you see the drag polar for our wing. This is turning the NACA data into a drag polar in 3 dimensions as shown. Once again, since there's no way to analyze a conic leading edge, we had to approximate the wing. The dimensions that we approximated are shown on the secondary screen. This came out to a CD min of about 0.0089. On the primary screen is a table of our wetted area. The inner column is a method used by Roscom to find the wetted area. On the outer column, we use the CATIA model to find the wetted area. To note that the Roscom method underestimates what the CATIA model shows, therefore all analysis is done using the CATIA model. The primary screen, you see a wetted area of Mach 0.2 or 0.2. This is close to our landing, projected landing. Therefore, this is our most critical case. You can see with the deployment of the landing gear shown in the upper curve, it increases our drag very slightly. To further analyze our performance as the parasitic drag on our vehicle throughout our subsonic and supersonic regime, the CD0 versus Mach is shown in the secondary screen. To note, the most drag we'll experience through these phases of flight is just over Mach 1 at about Mach 1.1, gives us a CD0 of just over 0.1. To next farther analyze our most critical case of landing, did a thrust required at sea level. The lower curve is coming into cruise, or not cruise, just coming into landing, and then the upper curve is with the landing gear deployed. We're projected to land somewhere around 190 knots, and this gives us a total drag of just over 16,000 pounds. On the secondary screen is a table of some of the key information pulled from the drag puller. Once again, the most critical case is about Mach 0.2 with the landing gear deployed. This gave us a CD knot of about 0.035 and an LOD of about 5.1. This is very comparable to other lifting bodies as well as the shuttle, which had around a L/D of about 4. And now I'd like to invite Chris up to talk about the structure and the landing gear. My bad, Nick.
Thank you, Eric. In design of the landing gear, we chose to emulate systems on similar aircraft, specifically that of the space shuttle. 3 constraining factors we put upon ourselves by the RFP and ourselves in the design process. The first of which was weight. We're limited to a 400-pound weight budget for the entire system. Number 2 was we considered system reliability, and 3 was size, as it is retractable gear needs to fit inside the vehicle. On the primary screen, you can see the design decisions made to address our 400-pound weight budget. First and foremost of which is we decided to eliminate any sort of hydraulic-powered systems. That includes any sort of deployment or retraction systems, as well as a hydraulic braking system. Instead, we decided to go with a completely mechanical deployment system. Additionally, the gear will not be able to retract during the flight, only deploy, and we chose to go with a proven electronic braking system. Additionally, we chose to go with more exotic materials than the typical steel that's used for landing gear systems. To replace most of the steel, we will be using aluminum. However, the drag brace in and of itself will be carbon fiber epoxy, as well as magnesium wheels. On the secondary slide, you can see the decisions we made to make a reliable deployment system. We decided to go with a gear that is connected by physical linkage to the airframe during flight. That physical linkage is severed by an explosive charge that is remotely activated by a personnel on the ground. This physical linkage ensures that the gear does not have premature deployment, as there is no retraction system. Additionally, we chose to emulate the space shuttle gear-door relationship in that they are physically and mechanically linked. On the primary slide, you can see some decisions made to address our size. Most prominent is that we decided to go with a 3-section drag brace for our main gear as opposed to a more traditional 2-section drag brace. And on the secondary slide, you can see the position of our gear relative to the rest of our vehicle. Moving on to our lateral and longitudinal tip-over and ground clearance criterion is specified by Roskin and Raymer. All angles are satisfied, and to note on the primary screen with the longitudinal angles, we do have a tip-over angle of 40 degrees. While this is over the 15-degree minimum requirement, it is significantly over. For our vehicle, this is acceptable as we do not perform a typical rotation takeoff, and that usually is what bounds the upper limit for that angle. Additionally, the CG location, as seen on the primary slide, is with no fuel and without payload, our ideal landing configuration. The primary slide, you can see the gear in its retracted position. To describe the deployment process, this physical linkage, which is, you can see is connected to a joint, is severed by this pyrotechnic charge. There's a system of torque springs within the main joints, which release some of their stress once this physical linkage is broken, enabling the gear to deploy. Furthermore, the gear is forward deploying, enabling the airstream to assist in this deployment. And last but not least, there is a mechanical locking mechanism to ensure that once the gear is at its fully deployed state, it does not retract any amount. The secondary slide, you can see the cross-section views of the gear within the nose section and the wing root. On the primary slide, you can see our internal structure. Our internal structure is broken down into 5 main components, first of which is the keel beam. This connects the V-tail and the wing internal structures. We also included tank braces, as you can see in purple. Those tank braces are woven into the tanks and provide structural support between the tanks. In combination with the keel beam, the tanks actually provide a reasonable amount of structural support for the vehicle, as they are ideal or nearly ideal pressure vessels, and any tank at any given time, the internal pressure does not drop below 6 atmospheres and can range up to 14 atmospheres. These tanks do provide structural support. Additionally, the torsional braces, seen in green, provide the skin size and shape integrity, as well as provide hard points for the PT1 to attach to. On the secondary slide, you can see our ghost view of the vehicle with internal structure highlighted in yellow. The primary slide details our material selection. Well, we decided to go with a MTM45 carbon fiber as provided by Cytec. This carbon fiber will be applied for the internal structure in its entirety, as well as the skin of the vehicle. Now, this decision was mostly driven by the fact that we need to be a light vehicle and therefore need a aggressively light internal structure. So the carbon fiber of choice provides a competitively low density while maintaining a significantly high structural capability. Now I'd like to invite Morgan to come talk with you about thermal protection and trajectory analysis.
Thank you, Nick. So in order to determine our thermal protection system, we need to determine the re-entry temperatures that the ambassador would see. Because we don't have any tools to actually get the actual re-entry temperatures of the ambassador, we had to look at similar spacecraft. The similar spacecraft that have re-entered the Earth's atmosphere, the X-37B and the Space Shuttle. However, since the X-37B is a classified project, all of the data is proprietary. So all of our re-entry temperatures are based on the Space Shuttle, which actually provides a more conservative estimate since it's larger than the ambassador. Now on the primary screen is some data from the first 2 shuttle missions. STS stands for Space Transportation System, which is the nomenclature used for all space shuttle missions. So the nose of the space shuttle during these 2 missions saw temperatures ranging from 2,000 degrees to 2,300 degrees Fahrenheit. And the leading edge of the wings saw temperatures, a max temperature approximately 2,500 degrees. Now on the secondary screen are some thermal images from 2 of the later missions on the space shuttle. After the Columbia accident, it was recommended that NASA create a thermal imaging system to monitor all of the re-entry temperatures of the space shuttle missions. Now, as you can see from the thermal images on the secondary screen, the max temperature seen was approximately 2,200 degrees. Now, in addition to these thermal images, there was also thermocouple data on board the space shuttles that accompanied these images. So for the STS-125 mission, the thermocouple data read about 2,200 degrees Fahrenheit. However, for the STS-128 mission, we were seeing temperatures about 2,500 degrees on the space shuttle. So this gives us a range of approximately 2,200 to 2,500 degrees for re-entry temperatures. Now on the primary screen are some of the options we had for thermal protection system, or TPS. We didn't go with the high temperature drag parachute because we have to be able to control our vehicle through all phases of flight. We also didn't go with aerogel because it's extremely brittle and it's better for internal insulation. So we decided to go with ceramic tiles and carbon-carbon, similar to the space shuttle. Now on the primary screen are the different options for carbon-carbon and tile coating options. The carbon-carbon is going to be used on the ambassador for the nose and leading edge of the wings and V-tail, as they were going to see the maximum temperatures during re-entry. We decided to go with the advanced carbon-carbon, or ACC, because it's more cost-effective and it doesn't lose any of the performance capabilities. It's actually developed after the Space Shuttle program. Additionally, for the tiles and coating, this will be used on the underside of the body, wings, and V-tail, because they'll see a little bit lower temperatures than the leading edge of the wings and nose.
For the space shuttle, they used the LI-900. It was very lightweight, but it was easily damaged, which led to their 4 to 6 month turnover rate. So we decided to go with the AETB-8, developed after the space shuttle program. It's just as lightweight, it's much more durable, and it's more cost effective. As for our TPS application, as you can see on the secondary screen, the tiles will be bonded directly to the vehicle. The advanced carbon-carbon is structural, so it will replace our skin, and the TPS weighs approximately 1,900 pounds. We also had to look at our orbital trajectory, which is the path the ambassador will follow throughout its mission. This was needed in order to determine our achievable altitude. We used MATLAB to create an optimization program to optimize our orbital trajectory. This took into account our gravity, mass, drag, and thrust. Thrust is what we're trying to optimize. Gravity takes into account the drag or the gravity, direction of gravity on the ambassador. Mass calculates the masses per gallon burns. Drag takes into account your coefficient of drag, the rotation of the Earth, the atmospheric density, and relative wind velocity. And your thrust is defines the direction in which the ambassador flies throughout the mission. Now, on the secondary screen are 2 phases of flight we had to define in this program. Now, on the primary screen is the plot of the different altitudes. So as we ascend into orbit, the apoapsis and periapsis of the orbit change. So as we fire the engines until our apoapsis reaches our target altitude of 87 nautical miles, at which point the engines are turned off and we are allowed to coast to our target altitude of 87 nautical miles. Once we reach that point, the engines are turned on and fired again tangentially or in the horizontal direction until periapsis approximately reaches our target altitude. As you can see on the primary screen, we reach our target altitude of 87 nautical miles. Now on the secondary screen is a depiction of periapsis and apoapsis. Another program we used to help verify our MATLAB trajectory code was AGI-STK. It provides a visual representation of our orbital trajectory. Given all the inputs, all the same inputs as MATLAB, it returns the same results as our MATLAB does. AGI-STK has the power to automatically optimize our trajectory, but we will be looking into this further in our detailed design. And now I'd like to invite Michael up to talk about verification of mission performance.
Thank you, Morgan. The first performance constraint that we had to verify was the landing distance constraint for the ambassador. This was done using Raymer's method and was found to be just over 8,400 feet with a flare altitude of 593 feet and a landing speed of just under 200 knots. The maximum flare angle is limited to 15 degrees on landing to avoid hitting the nozzles during the flare maneuver. One of the other things we wanted to verify was the aerodynamic capabilities and stability of the ambassador. Since most of our design equations aren't typically used for a lifting body configuration, we wanted to make sure that the ambassador was still stable in flight. We wanted to account for some things like the interference of the fuselage with the wings, with separation and four-body vortices. So we decided to build a flight test model to verify our stability. On the secondary screen, you'll see a picture of the first flight test model we built with a single vertical tail. This was built out of foam and tested with a variety of different static margins by hand launching it. And it was found to be unstable in pitch in all configurations with different static margins. Therefore, we made the decision to switch to a V-tail design. You see the final model displayed here. That model was hand launched and was found to be stable, so we made the decision to proceed to air launch testing. The model was lifted on top of a larger remote controlled airplane and brought to heights of about 150 feet. The first test revealed that the model was very unstable in roll. This is typical of many lifting body designs. This was corrected by adding a 6-axis gyro to the elevons, and that corrected it and was found to be stable in pitch and roll in subsequent test flights. We've accomplished several successful landings with it and has very good flare characteristics. Now I'd like to invite Brandon and Veronica to discuss cost, labor accounting, conclusions, and recommendations.
Thank you, Michael. So first I'm going to go over our project cost estimate. Now we worked heavily with LaunchTech for this because we wanted to come up with a cost for the entire system. Now the entire system, as far as the RFP is concerned, we need to be able to manufacture at least 3 sets of each vehicle. So that's 3 PT1s, 3 ambassadors. So that's the cost we initially came up for. Now it's pretty difficult and there's not many tools available to us, especially as students, to come up with a cost for a spacecraft vehicle. So what we did is we used Raymer's method to come up with the cost for the PT1, and we assumed we were going to be more expensive as a space project, multiplied that by 1.5 to come up with the cost for the ambassador. Combining that all together for 3 whole systems is $13.5 billion for the project. Now, in addition to this, we also had to come up with a cost estimate for a launch, because we won't necessarily be selling our vehicles, but we'll be selling a spot in our payload bay to carry satellites to orbit. So we came up with an estimate of about $1.8 million per launch. Now that's taking into consideration licensing for launching, salaries for both people working for Genesis and LaunchTech, as well as maintenance on the vehicle. We will have to replace the nozzle extensions every 4 flights, and we'll have to replace the engines every 16 flights. So that's taking all of that into consideration. On the primary screen, you can see some labor hour breakdowns. Now this is just for the Genesis team. The dotted line in blue depicts the predicted hours that we would spend working on this project throughout the semester. Now this was estimated by assuming all the students would spend 2 hours outside of class for every hour in class. The red solid line depicts the actual hours we have worked on this project, and we are slightly over. On the secondary screen, you can see the breakdown of 5 different categories. We decided to split the hours of our time for this project. You can also see an overview of the cost and hours.
So now on the primary screen, you can see a visual breakdown of those hour categories, and on the secondary screen is their associated cost breakdown. Now, the largest portion of both of these was spent on professional development. This consists of time spent in class, and it also consists of time spent outside of class researching different methods and ways to make this project feasible. And now just to give you guys some conclusions to wrap everything up here. One conclusion that Genesis drew is that we have an aerodynamically sound vehicle. All of our analysis showed that we would be able to be stable in all of the phases we expect to be flying in with the addition of a flight control computer. And then we verified this with our flight test model as well. Some other conclusions we drew was that we have an aggressively light structure, which means it would be difficult to manufacture a real-life version of this vehicle. And we also have a low orbital altitude, meaning that any of our small satellite payloads wishing to go to a higher orbit would need an additional propulsion system added to it. Both of these affect the marketability and practicality of our vehicle, and they're both caused by our propulsion system not being as efficient as we would like it to be. So in order to remedy this, Genesis would recommend designing a more efficient propulsion system were this to be built in the future. A more efficient propulsion system would lend more weight to be used as structure and could also carry us to a higher orbital altitude, eliminating the need for that satellite payload to have its own extra booster attached to it, thus increasing our marketability and our practicality. And then these are a few of the individuals we'd like to thank for their continual help throughout the semester designing this project. And we'd also like to thank all of you for coming out today to view our presentation. And with that, are there any questions?
Hello. There we go. Really good presentation. Really good job on your logo. I don't know who designed that, but that looks pretty good. So I have a bunch of questions, so I'm just going to try to limit to what I have. So for your lower orbit, what are your altitude bands for that? It's not just one set altitude, is it?
So the RFP, the requirement was we had to make it to low Earth orbit. Because our propulsion system is not very efficient, that's one of our recommendations, is to come up with a better propulsion system. We can actually only make it to the minimum altitude of low Earth orbit, and that's 87 nautical miles. Now that is calculated with our maximum payload of 332 pounds. Now that could go up slightly if we vary our payload. So if we're taking up a smaller one, we could go up a little higher in orbital altitude.
Did you guys look at what separation distance was required between the Ambassador and the PT-1 before it would launch its rockets?
No, that wasn't something we directly looked at. We weigh 75,000 pounds at launch, and our wing doesn't provide enough lift in order to accommodate or to provide lift at that point. So we assumed that we'd be falling away from the PT-1 fairly quickly, such that we could just focus on igniting the engines almost immediately. Should anything go wrong, the PT-1's crew capsule is an escape pod, and it can jettison and get away from any mishaps that happen.
And in our trajectory calculation, we do say for the first phase, we're going to fire straight forward for about 5 seconds to avoid any collision with the PT-1.
Okay. I have some questions about the electronic system. I'm a flight tester for stuff that falls off airplanes, so that's kind of one of my things. I'm assuming that there's a battery on this. What's the battery life?
So we didn't get into that level of detail. We were instructed we could actually, for the most part, ignore a lot of the electronic part. That's why you didn't see in the actual configuration. You just saw where it was located rather than electronics themselves. So being as more of an AE structural team, we looked more at the structural side of the vehicle. Now there were some details we went into. I don't know if you had, did you have a specific battery you picked out for the vehicle in fixed equipment? Okay.
A battery life wasn't determined. What we were going to use hydrogen fuel cell batteries and lithium ion batteries. The way we did the battery analysis was our power consumption needs, but battery life was not looked into.
Yeah, the reason I ask that is your weight. Your margin there was 2.5 pounds, which isn't very good, and batteries are heavy. So for whatever your mission duration is, looking at battery life, how long your batteries have to last, and therefore what the weight would be for that. Are you going to have this thing electrically connected to the PT-1 prior to launching it? That way you make sure it runs through like self-test, make sure all your systems are good, but before it leaves?
That would be the idea, yes. But again, we don't have any electrical engineers on this project, and we didn't have the manpower to really focus on the systems level components setup of our vehicle.
And then, on your model that you did with the flight testing, you guys had mentioned before that the V-tail was all movable. But I noticed on your model that it's not an all movable V-tail there. Also ailerons. Do you have any ailerons on your model that move?
Yes, the full span ailerons are modeled, and we actually on the model call them elevons because we use them to help with pitch as well during flight. And so I don't think on the real vehicle we would use them as elevons, and that's where the all moving tails come in. But another reason for that is just with the scale of everything, the all-moving tails would have been very sensitive, which makes it difficult for just a remote control pilot to fly. So we stuck with just elevators for that.
Just keep that as a note, that that's a fairly large difference between your flight test model and what the actual model is going to be.
Yeah, we did an analysis to figure out how sensitive our pitch would be, and in order to perform our flare maneuver, we would only need to move the vertical tail, the V-tail, something like 1/4 of a degree. So it's extremely tight, and we realized that. But we think the best solution to this is most of re-entry vehicles have a body flap underneath the rocket nozzles to shield them from re-entry and also to help augment pitch control during landing. And we think we could use something like that to help desensitize the pitch a little bit when we come into land. However, we don't really have any real way to analyze that.
My next set of questions is if there's problems. The first problem that you could potentially run into is you separate from the PT-1 and your engines don't work, or only one of them lights. Are you able to make it back to land at the airport in that kind of configuration, heavy with your full payload, and just gliding back down to Earth?
So we do need both engines to get up to the desired altitude. So what we would do is, in an abort scenario, we would actually dump all of our fuel. And then we would be able to glide back and land on the runway. So that was one of the things taken into consideration as far as safety goes.
And so back on slide 49, A and B, one thing that would be helpful there, and this is just a suggestion, is with the landing gear. Is having an arrow somewhere on there that points to where the forward part of the spacecraft is. That way I know kind of like what I'm looking at, because right here I don't really have a good situational awareness of what I'm looking at.
That's a really good suggestion, so thank you. And just for your clarification, they're actually opposite of each other. The upper picture, the forward part of the vehicle is to the left, and the bottom picture, the forward part of the vehicle is to the right, correct? No, they're both going to the left? Okay.
Yeah, they're both to the left.
Okay.
That was a suggestion there. And then, I don't remember what slide it is. It was talking about the drag at landing, and you guys used 0.2 Mach. For anything like less than 0.3 Mach or something like that, it's a lot easier to convert over to knots to just have an idea of the airspeed when it's that slow. And that's all I got, but really good presentation.
Thank you.
Again, good job. It was a good presentation. Are you guys going to have any cameras on the vehicle to make sure that you're off the PT1 or to watch the deployment of your payload?
We will have a camera. That's actually how we're going to fly the vehicle, because it's going to be kind of like a remote control. Somebody on the ground will be flying the vehicle, so we will have cameras installed in order to control it and make sure everything's going properly.
Okay, so there's no autonomy for any of the flight?
It will have to be autonomous for most of its flight, especially during re-entry. There's a blackout that will occur during re-entry. Ionized gas around it will prevent any signal getting to or from the vehicle. Any pilot link would mostly be on approach to the runway. Now, it's likely we could have it autonomous the entire duration of the flight. However, we would have that pilot data link for landing as a backup.
And just to clarify for me, was the release attitude from the PT-1, was that level flight or nose high or anything?
It was assumed to be level flight.
Okay. Slide 31, Bravo. Kind of similar. At first I didn't know what I was looking at here. It took me a second. So I believe that's the nose of the aircraft. Okay. And 38 Alpha. So for me, it's nice to have this graph, but I don't really know what's going on with the vehicle. So I think it would be good to have, side view of the vehicle and show how the CG changes in relation to the vehicle, because even though it's, in front of the aerodynamic center.
Yes, that's correct.
Yeah, it's hard to, I guess, see that, because I don't know if it's, the nose is 0 or...
Yeah, the nose is defined as the 0 position, and that's not, typically the textbooks we have don't show a side view of the aircraft with it, but that's a really good suggestion that would help make things easier to see on this.
Just to show the difference.
Yeah.
And then 46 Alpha. The use of non-traditional gear materials. I know you guys couldn't really do a cost analysis, and it was just kind of an assumption 1.5 times the cost of the other craft. But I don't know, would use of non-traditional gear materials, do you think that would drive up the cost more? Or
Absolutely. It would probably be a very expensive landing gear setup to get it as light as it needs to, which plays into our difficulty to manufacture such a light vehicle. That's where more efficient engines would give us more weights to get the cost down even more.
50 Bravo. I guess off the top, I don't know. So with the skin and the structure, did you guys consider, like, I guess, stringers going along the sides or the top? I don't even know if that's the right terminology, stringers, to be honest.
Yeah, so we'll go ahead and hand this over to our main structural team member here. This is Nick.
Good question. We actually, because we do not have the tools to analyze such a geometrically complicated structure that is carbon fiber, we decided, instead of modeling as many stringers as you might typically see, we decided to go with more solid bodies, like in the torsional braces, a lot thicker than they would need to be, so that mass would be distributed among stringers. However, as opposed to an aluminum body aircraft, there's much more flex in the skin with the carbon fiber, so you would need less stiffeners. So that was our thinking on that, along those lines.
Okay, thanks. And then 63 Alpha Bravo. Just wanted to comment. Good job on. I think it was ambitious to do the flight test. It kind of, gives me warm fuzzies about your design. I'm sure it gave you some too. But I think that was a good addition to your research, and just kind of proving to yourselves, or at least questioning, hey, does this really work? Going forward, kind of referring to the last slide I talked about, I think it would be good to see an ANSYS model of the structures, and perhaps, I don't know, it might be hard to do with skin too, but just because it's so unique, and just to see how it interacts. I don't know how you would do it, but it's not my problem. So, that's all I have. Thanks.
Thank you very much.
Thank you.
This one has no comments. Most of what I want to say is comments for the next time you do this. On slide 6B, you want to talk about that allowable risk to the public and what that money means. Same comment to the other group. Anytime you get, and you got a lot of them, anytime you got big groups of tables of numbers, those need to be converted to some sort of picture. These things can be pie charts, they can be annotations on a picture of your airplane. Do something to make it not a table. Love your choice of configuration. I think it's very low risk. It represents the product of what I perceive to be really good research into what your options were. I'd like to see a little bit more discussion about the variations between dropping it from under the wing, dropping it from just having it on top of the wing, dropping it from the fuselage, and what the implications of those initial choices were in the outcome of your airplane. Those initial steps determine most of the cost, most of the risk in the whole program. And you had some really good examples. I would love for you to talk about those a little bit more. The people who did the payload bay, I was very concerned about. You guys are just pyromaniacs. Y'all love pyrotechnic devices. I think more cold gas would be safer, might take a little weight. Man, y'all want to just blow everything up their chance you get. I was worried about using springs to separate the payloads in space, recording velocities without any way to control them. That kind of worried me from that. Somebody who did the access to the payload bay, you got all this wonderful CAD. Why not show me a perspective of the vehicle and show the getting things in and out? That would have been really nice. Slide 17AB is typical for the tip. Airfoil would be thinner section than the root. Y'all reversed that. Not sure how that was. We're going to talk about that. What is a Q limit? What is it? You know?
It denotes a limit that the vehicle can perform a fly at.
Probably want to show a Q versus altitude and Mach map.
Yeah, we have a table that we were putting together, but
I didn't say a table.
yeah, that's how we were initially calculating it, and it was a lot of linear interpolation from
That's
space
fine.
shuttle
Nobody
data.
cares. You just put the dots on there at every 10,000 feet. That's good enough.
Okay.
And we'll see the trends, but I'm worried about the Q limit is the same no matter what altitude you're at.
That Q limit was driven off tire blow speed, so we can't touch that.
Yeah, this needs to be beefed up. Q part of this is good. Talk about configuration being good. And same thing, comment for the other group. Need to see what your wind tunnel plan is. The whole product of this is being ready to go to next semester. How you can do this. I'd love to see some idea what your test plan looks like. You brought up the body flap late in the presentation, but you'd already talked about longitudinal stability already all the way back to 24. That needs to go all the way forward. You're going to use that in the body flap for pitch control. Somebody needs to show me that. Love the stuff about the rockets. That's so much fun. I'm not a space guy. I really liked all that. One problem I had those pictures those too, but you said you needed 4.
4 was for the RL10 engine. Now that we switched to the RL60, we only need 2.
Okay, well, I'm saying ambiguous. And that's how you say that. Slide 30 something, you said smaller. That means volume is more important than weight. So
So you're talking for the RCS tanks, correct?
Yes, I'm talking, yes.
So we also want to minimize the size of the vehicle because if we increase the size of the vehicle, that will increase weight. So that was the best option. We had a couple other small spaces to be able to fit those tanks.
Be precise in your language. When you say smaller, you mean less volume. When you mean lighter, you mean less weight. Okay, you can be vague and ambiguous. Otherwise, slide 31B, I don't see any way to create a vector in the down direction or in the up direction. That whole slide was vague and ambiguous. You want to fix that. Michael, was it you that gave me 6 significant figures in a decimal place on a weight estimate on a preliminary? I told you that. Okay, y'all watch your significant figures, please. Back to the CG travel chart, you're showing 7 feet of CG travel on this thing. That's a lot. You may need to manage that a little bit better. And again, I would echo his comment, show that big scale on the vehicle so we can get a feel for the CG travel relationship to where the center of pressure is. So the coefficient of drag versus Mach, you certainly got the right shape, you got the right magnitude, that'd be great. Not sure, I believe slide 43A, you want to work on that. Just get that, go to 50A and B. Just love some of this, but I echo this thing, you got to show stringers. You might even want to put a top key on this thing to prevent flexing in this direction. Love your cat. Okay, who did that? Okay, that's just fantastic. That goes for you like that, showing all the internal components and stuff. That's just really good. More of that, just really, really good. Don't believe that you only got 1,800 pounds for your thermal protection. That's what you got. That's what you got. Somebody said something about detailed design. When it comes to detailed design, you are making parts. You need to be past resizing, changing. You don't go in making parts in the detailed design phase until you have flows. Love the flight testing. But when you get ready to do your wind tunnel model, I want to point out some things that are going to be real key. The radius of curvature around the edge of that body is going to be important. The shape of that nose is going to be important. Okay, I don't know how many parameters you're going to be able to look at, but you're certainly going to want to put that body flap in there and check your pitch control. You're certainly going to want to check your lateral directional stability. Like he said, this type of body is notorious for having absolutely lousy rolling and off. You're going to show me hours of cost, you need to show me rates. Other than that, I just have a question. Anybody else have questions? We probably have time for one.
I got 2 really quick questions. Was there a specific place you guys were going to land after re-entry?
Yes, so we're actually launching and landing at Puerto Rico, and the reason for that is the closest U.S. territory to the equator. So that will help minimize our delta V, or change in velocity, to get to orbit.
And I don't recall seeing a cost comparison, and it would be tough to get this thing to go through to the next phase if they don't know if it's cheaper or more expensive.
That was in the very beginning of the presentation. Right after going over the similar vehicles for the design, we had the weight and cost comparison there.
Thank you.
The only other thing I can think of is if you're gonna do an 8-hour turnaround, you have to have 2 pits. Thank you very much. I thought that was great.